Good afternoon, class. In today's video, what I wanted to do is to take you through an example of energy, and this one will go through all three types of energy. We've got potential energy, work, and kinetic energy. The other bonus feature of this is that I'm going to be invoking conservation of energy as well. So hopefully that'll give you some ideas of how to handle the different homework sets, because while these aren't specifically homework problems, they are useful in the sense that because I give you the formula and you see the work that's been done throughout it, it should be easy enough to plug in the same values and continue your work through all of the homework sets as well. So let's get through this, and it's a nice problem because it's a one question and it's got three parts to it. So here we go. I've got a ball of mass 1 kilogram. It falls to the ground from a cliff on Earth that is 30 meters tall. So there's several things that are broken down in here, and I want to make sure that that's pointed out. First, we've got the mass. If you know that it falls to the ground and it's on Earth, that tells you something because that means that the acceleration due to gravity is 9.8 meters per second squared. I don't have to write that on the paper, or at least on this question right here, because it's already implied, because you already know that value because I've said it's on Earth. Okay, and of course we've been given a height as well. So let's go through the first question. What was the ball's potential energy at the beginning of, before it fell? And so you would say, okay, well, we're going to use potential energy is equal to mgh, and then we're going to take all of the numbers that we've got from the problem, and we're just going to plug it in and go for it. So potential energy is 1 kilogram times 9.8 meters per second squared times 30 meters to give you a number of 294 joules. So that would be how to do the potential energy portion of this question. And notice, of course, I'm using the shortcut method to figure this out. So the next question is, so how much work did the ball do when it first contacted the ground? So you'd have to take the work that it did. So you need the force that it applied to the ground over the distance that it fell. Okay, well, let's check that out. Work is equal to force times distance. So, well, what is that force? The force is the weight of the ball as it smashes into the ground. So then that's mass times acceleration due to gravity. Oh, I think I've seen this before. I think all of us have seen this before, because then that's 1 kilogram times 9.8 meters per second squared times that distance that it fell, which was 30 meters, and so you get 294 joules. It's almost as if when we're lifting something up off the ground, the work and the potential energy gains are exactly the same. Interesting. Now, and this is true only when other factors are not taken into account. For example, if I lifted this ball up to the top of that cliff and then dropped it, that's one thing. You don't have to worry about things, as long as you don't consider things like drag, air resistance, or drag and air resistance. If you don't consider things like other variables, like maybe the wind or something when this ball is falling, as long as you consider everything basically a vacuum as it's falling, then these two are true. However, if there is friction, then this work being equal to potential energy is not exactly true. There are going to be a couple of exceptions when you include those other things. For example, let's say you've got a little bit of an incline here, and I push a block up the incline. Whatever that height that I pushed it up would be how much work was done, and also how much potential energy was gained during that time. However, if this ramp has friction on it, then while the potential energy gain would be from here from wherever I started to this new height, I'd have to take into account all of the frictional forces that went into it and all the frictional work that I would have to have done to get it to that height. So that's what I mean. There is a little bit of a difference. And what I can do is make another video where I actually do take into account friction on a ramp like that. So maybe that'll be for a future video. So now that we've gotten the potential energy and the work, now we can talk about the speed at which it falls to the ground. Now, of course, this deals with kinetic energy. So we're going to use the equation. Kinetic energy is 1/2 mv squared because we want velocity or speed. But we don't know what the kinetic energy is unless conservation of energy is taken into account, where we know that kinetic energy would equal potential energy at least when the ball first, like say this is the bottom of the cliff, when the ball first touches the cliff bottom, not when it bounced, not after it hit the ground and stopped, when it was falling and it first touched the ground, that point is where I'm measuring what the kinetic energy is, and which is at that point would be the same as the potential energy, and that's how I can measure the velocity of the ball as it smashes into the ground on the first hit. We're assuming no bouncing or anything like that. Again, if you want another video about if it does bounce, that's another one we can cover in a later video as well. So let me know if you'd like to see a video like that. Okay, so we're going to say kinetic energy is equal to potential energy, and I already know what that is because I figured that out earlier in part A of this problem. So we're going to put 294 joules is equal to 1/2 times the mass, which is 1 kilogram, times velocity squared. Okay, well, I'm trying to isolate my variable here, so I'm going to, velocity squared is being multiplied by 1/2, so to isolate the variable, I'm going to do the opposite operation that's being done to it. So the opposite operation of multiplication is division, so I'm going to divide both sides of the equation by 1/2. And so I get, from 294, I get 588 meters squared per second squared is equal to v squared. Now, of course, I don't want velocity squared. I want velocity, or I want the speed. So what I'm going to do is I'm going to square root both sides of the equation. So I'm going to get the square root of 588 meters per second. Now, of course, why is this speed and not necessarily velocity? Because we know it's going down. We can look at this problem. It's falling. It's on a cliff and it's falling down. That's for sure going to be, the direction would be down, so we could figure out its velocity. But I really only want its speed and that's why I left it as positive, because speed is the absolute value of velocity. So that's why this is just the positive number of positive square root of 588 meters per second. So that's how to handle a problem that deals with not just kinetic energy, but also with conservation of energy. You've got now you know how to deal with a problem that deals with work, force times distance, and regular potential energy, MGH. So hopefully that, while this is a little bit of a longer example video, what I hope is that you understand this should cover at least 3 different types of example problems that could be done on your homework. So with that, good luck in your studies, and may the force be with you.